Hey everyone, welcome back to Linear Algebra. This is going to be part B of lecture 22. And so where we had left off, we had just we just finished writing the proof of the dimension theorem out. And it was a tricky proof. It had some kind of subtle ideas there, but the theorem itself is relatively easy to understand. You've got these two subspaces, and you have each of them will have a particular dimension, and the sum of the dimension of these two subspaces, the kernel and the range, is equal to the dimension of V. Right? And so let's talk. What we're gonna do next. We're gonna talk through a corollary and some add-on theorems, and we're gonna go through a handful of examples to make sure we can see this dimension theorem playing out with real examples. So let's start by just knocking out a corollary here. So if L is a linear transformation from V to W, so if L is a linear transformation and V is finite dimensional, okay, it's finite dimensional, then the dimension of the kernel of L, okay, is going to be less than or equal to the dimension of V. That's pretty straightforward. And the dimension of the range of L is less than or equal to the dimension of V. Okay, so the first one is obvious, right? We know that the kernel is a subset of V, and so clearly the dimension is less than or equal to the dimension of V. That we know from a previous example, but the second one is less obvious. Well, it's obvious once you've seen the dimension theorem, but just in general, you wouldn't have assumed this to be true absent the dimension theorem. And so, in particular, the range, we know, is a subset of W. It's not a subset of V, but the dimension theorem forces the dimension of the range to be less than or equal to the dimension of V. Okay, so something to beware of. Okay, beware. So, if you have L from V to W, linear transformation, it's not necessarily true that the dimension of W is less than or equal to the dimension of V. It's not necessarily true that the dimension of W is less than or equal to the dimension of V. In fact, it's not true in general, right? We could easily find examples where this didn't happen, right? It's very easy to concoct an example where the dimension of W is larger than the dimension of V, right? So for example, let's say V is equal to R3 and W is equal to R4. I can come up with a linear transformation easily from R3 to R4, right? All I have to do is say, let's let L be the linear transformation of x, y, z that maps to x, y, z, 0, right? So this is in R3, this is in R4. We know that the dimension of R4 is 4, the dimension of R3 is 3, right? And so this is a counterexample, right, where the dimension of W is not less than or equal to the dimension of V. Right, and so the only reason we bring that up is because you may think that this relationship between the range and V would imply something of the sort about V and W, but it doesn't. Okay, just a caution there. Okay, let's take a look at an example. Let's take a look at a nice example. Let's let L be the linear transformation on n by n matrices to n by n matrices. Right, so it's really a linear operator here. And let's say this is given by L of A equals A plus A transpose. Okay, so I take a matrix A, and when I apply L to it, I am taking A and adding to it its transpose. So hence, in order for this to work, these have to be n by n matrices, and obviously they're going to map to n by n matrices. So this is fine as set up. Now, what is the kernel? What's the kernel of L? Well, it's going to be the set of A in M and N, okay, such that what? Well, we're going to need A plus A transpose to equal the zero matrix, the zero n by n zero matrix. Okay, and so what are these matrices? What are these matrices in the kernel? Well, basically this condition here implies, right, if I have A plus A transpose equals 0, that implies that A equals negative A transpose, right? Just doing a little algebra there. And so what kind of a matrix must A be if it's equal to its negative transpose? These are going to be the skew symmetric matrices, aren't they? Well, so that's going to imply A is a skew symmetric matrix. Okay. So these are the skew symmetric matrices. So the kernel is all of the n by n skew symmetric matrices. All right. What about the range? So the range is going to be the set of all matrices of the form A plus AT. It's going to be all of the A plus AT matrices. Okay. Okay. So think about this for a second. Let's let B be the A plus A transpose matrix. Okay. So then what happens when I transpose B? So B transpose is going to be equal to A plus A transpose transposed. And we know that that is equal to A transpose plus A, right? So kind of, you can think of it as distributing the transpose, right? And the transpose of a transpose is back to A, right? So you get this. And so this is equal to what? Well, this is again just B, right? A transpose plus A is the same as A plus A transpose. The order doesn't matter here. And so that's again B, right? And so B must be symmetric, right? It must be symmetric if B transpose is equal to B. Okay, so it's symmetric. And so we know then that the range of L is going to be some subset of the symmetric n by n matrices. Right, it's going to definitely be all of the elements in the range will be symmetric, but it may not be all the symmetric matrices. We don't know. And so let's look at what we can do here, right? So if B is symmetric, then we can do this. We can say L. We can apply linear transformation to 1/2 B. Right, and that's equal to 1/2. I can factor the constant out here, and that's going to be equal to 1/2. Just crossing that out here. And so when I apply the linear transformation to B, I get just basically B plus B transpose, right? Okay, and since B is symmetric, that's going to be the same thing as 1/2 B plus B, since B is equal to B is equal to B transpose. And so that means this is equal to B. Okay. And what does that mean? Well, then that means B is in the range of L. And so what does that mean? Well, that means that the symmetric matrices is a subset of the range of L. Okay, and so, here you've got one direction. The range of L is a subset of the symmetric n by n matrices. Here you've got another direction. Symmetric matrices are a subset of range of L, and so they're equal. Right, so the range of L is equal to the set of symmetric n by n matrices. So what kind of started out as a sort of seemingly simple linear transformation, we see is kind of anything but actually pretty interesting, right? So the kernel are the skew symmetric matrices, and the range is every other symmetric matrix. Okay, so very interesting example. Interesting. Now, what about the? Well, now we'll move on. We'll move on. Okay, so that's an interesting example. Okay, and so what about the? How do we find the kernel? So the previous section we talked about the matrix of a linear transformation. What we want to do next is we want to think about how do we find the kernel given the matrix of a linear transformation, right? So given that we know that what the matrix of the linear transformation is, how do we find the kernel? Okay. So let me write that down. How to find the kernel from the matrix of a linear transformation. How do we do that? Okay, and so let's say we're given some linear transformation R from Rn to Rm. Okay, given by L times the vector x equals A times the vector x. Okay. Now, here in this context, A is a fixed m by n matrix. A is a fixed m by n matrix, and x is obviously a vector in Rn. Okay, so given this, what we want to do is we want to know how can we think about the kernel, right? When all you're told is you've got some matrix A that defines a linear transformation. So what is the kernel, right? Well, let's go back to the definition. The kernel would be the set of all matrices in Rn that map to 0 when multiplied with A, right? And so what that amounts to, it's going to be the solutions to the homogeneous system A times x equals 0, right? Right, so the linear transformation is just A times x, and the kernel is going to be everywhere where that is equal to 0, that product. Okay. And so how can we think about this? Well, we're going to naturally, given that we're talking about a matrix here, we're going to need to pull in the reduced row echelon form. So let's let B equal to the reduced row echelon form of A. Okay. Then we know that a basis for the kernel can be found by solving for particular solutions. Okay. Then a basis for the kernel. So a basis for the kernel can be found by solving for particular solutions to the system. Well, AX equals 0, but better BX equals 0, right? And why B? Well, B is a reduced row echelon form of A, right? So in practice, it would be best to reduce A until you get B, and then you can find particular solutions from bx equals 0. And so how would we do this? Well, we'll kind of systematically set each independent variable in this system equal to 1 while setting the others to 0, right? So let me just write that down. Then a basis for kernel can be found by solving for particular solutions to the system bx equals 0 by, we'll do an example of this in a moment, by systematically setting the independent variables equal to 1, sorry, and the others to 0. Okay. Right, and so given this, we would know the dimension of the kernel is going to be equal to the number of independent variables. Right, because I mean, you're going to have a basis vector every time you plug in a 1, basically, and the rest of the zeros. You're going to get a basis vector out. And so the number of independent variables is going to dictate how many basis vectors you have. Hence, the dimension will be equal to the number of independent variables. Okay, let's do an example of this, because this may seem a little confusing. It's relatively straightforward if you actually do an example. So we're not going to do the row reduction, but let me give you the matrix and the reduced row echelon form, and I'll let you confirm that if you like. That is what our REF looks like. So we'll let L, in this case, be from R5 to R4. Right, and that means we're going to have a 4 by 5 matrix. And so it's going to be given by L of x equals AX. And so let's write out A. So 8, 4, negative 2, 6. 4, 2, negative 1, 3. 16, 10, negative 5, 15. 32, 22, negative 11, and 33. And 0, negative 4, 7, negative 7. Right, so again, I just give you this matrix because I mean I want you guys to be able to go from end to end on this example. You start with A, reduce row echelon form of A, and so when we do reduce this, we get our B. That's just the reduced row echelon form of A, and so what you would have there is 1, 0, 0, 0, and then 1/2, 0, 0, 0, and then 0, 1, 0, 0, and negative 2, 3, 0, 0, and then 0, 0, 1, 0. Okay, so that's the reduced row echelon form here. And so you can see we have pivots in column 1, 3, and 5, and the others are independent variables, right? So given this system, given this reduced row echelon form, we have, so given B equal RREF of A, we can see that the system Bx equals 0, that's going to have an independent variable in column 2 and 4. So independent variables x2 and x4. Okay, and then the system itself would look like this. You could, extract this from the reduced row matrix here. x1 will be equal to negative 1/2 x2 plus 2x4, and then x3 is equal to negative 3x4, and then x5 is 0. Right, so that's what the system kind of looks like when we row reduce it. And so we can construct two particular solutions, right, in this case, because we have two independent variables, x2 and x4. And so solution 1 would be found by setting x2 equal to 1 and x4 equal to 0. And so in that case, you would get a vector that looked like this, right? If I set x2 equal to 1, then this is negative 1/2, and then I set x4 equal to 0, this is 0, so I get negative 1/2 for x1. And then x2, of course, is 1, right? What about x3? Well, it's going to be negative 3 times 0, so it's a 0. And it turns out x4 and x5 are 0 as well. Right? So here's one of the basis vectors. Sorry about that. Here's one of the basis vectors. And we can get the other basis vector in a similar way, except in this case we'll set x2 equal to 0 and x4 equals 1. Right, and we'll get a second vector and confirm this, but what you end up here with is 2, 0, negative 3, 1, and 0. And this is the other basis vector. Now there are no others, it's just these two. Okay, and so the kernel of L is going to be equal to the set of all vectors. Well, it's going to be the set of all, so the set of all vectors where you have A times V1 as defined above here, plus B times V2, such that A and B, these are just real valued constants, scalars. Okay, so that's what the kernel looks like. Okay, and you could write it in different ways. It's possible to write it as a single vector. All right, let's do that. How would we do that? Well, what we would say is we'd actually run the numbers here. So A times V1 would be A times negative 1/2 plus B times 2, right? So you could write it like this. It'd be negative 1/2 A plus 2B. That's the first component. And then it would be A for the second component, and then 0 minus 3B for the third component, and then B for the fourth component, and then 0 for the fifth component. So all the vectors will have this form, and then A and B are again real numbers. That's just another way to write it. It's the same space, but slightly different way to write it. Okay, and so that's an example of how to find the kernel when you're given the matrix of the linear transformation. So let's recap all of that. How did we do that? Let's kind of write that out. Let's recap the process. So the general method for finding a basis for the kernel of a linear transformation. Okay, and so let's what's the setup here? Let's let L be the linear transformation from Rn into Rm. It's a linear transformation, and of course it's given by L of x is equal to A times x for some matrix A. Okay. All right, so just basically the setup that we just talked through. So then to find a basis for the kernel, what do we do? Well, step one is we have to row reduce A. Okay, so find B, which we'll say is the reduced row echelon form of A. Okay, row reduce A. And then the second step, once you have the reduced row echelon form of A, solve for a particular solution for each independent variable in the system. Solve for a particular solution for each independent variable in the system, right? And you would want this to use the system bx equals 0. Obviously, you found b, so you'd want to use that. Okay. And then, right, basically once you've done that, you'll have, if you have k independent variables, then you'll be able to do this k times, and you'll arrive at k different basis vectors. And the set v1, v2, dot, 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 vk is a basis for the kernel. Okay, perfect. And so that's the basic idea. Okay. Now, so recap. Given the matrix of a linear transformation, this method here tells you how to go about quickly identifying a kernel. Now, whether it's quick or not, if you're doing this by hand, is not really necessarily true, but it's a discrete sort of method that can be applied in any case. You can always use this, and it works in general, right? And so this is for finding a basis for the kernel. What about a basis for the range? We want to do the same kind of thing. We want to be able to find a basis for the range given the matrix of the linear transformation. Okay, so similarly, let's now talk through how to find a basis for the range of a linear transformation given a matrix. Okay, given a matrix for the transformation. Right, so again, same setup. Given L from Rn to Rm, defined by L of x equals A times x. So in this case, the linear transformation is completely determined, right, by the image of the basis, right? If you have the domain of the linear transformation, all you need to know is give me a basis for the domain and let me see what happens to what the image of that basis is, right? So basically, in this case, given any basis, right, will work. And so obviously the one to choose is the standard basis. So given the standard basis, E1 through En, right, we know that, the set L of E1 dot 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 L of En spans the range of L. Right, so we know that that's true, but the linear transformation of the ith basis vector here is going to be the ith column of A, isn't it? Right, this guy here, this is the ith column of A. Well, that's just, you can just think about what's going on with the linear transformation. It's the way it's defined, right? Okay. So the columns of A are going to therefore obviously kind of span the range, right? Right, so you could say that implies that the columns of A span the range. Okay. Right, and so let's kind of write that in a little more concise way. So the range of L is equal to the set it's equal to the span of the columns of A. Okay, and so that's the idea. That's kind of the whole idea about how we can determine what the range is here. Now, so what is the technique? So here's the general method. And then again, I guess I should say for finding a basis for the range of a linear transformation. Okay, and this is sometimes actually called the range method. There are different ways to do this, but this is, I think, the most straightforward. Let's let L be a course from Rn to Rm given by L of x equals a times x. Okay, and this I'm going to shorten up some of the prelude here. I mean, obviously we know A is the fixed matrix of the linear transformation. So then to find a basis for the range of L, what do? It's a two-stepper, very simple. First, find B, which is the reduced row echelon form of A. Okay, and then the second step, which actually has a couple steps, form what we want to do from given B is we want to form the set of the columns of A whose corresponding columns in B have non-zero pivots. Okay, so let me write that down. So form the set of columns of A whose corresponding columns in B have non-zero pivots. Okay, and that's going to be the basis. This set is the basis for the range of L. Okay. Okay, now let's do an example. All right, make sure that that's clear. Right, but it is a two-stepper, basically. You find B, just reduce row echelon form of A, and once you have B, you're going to be able to clearly see what columns are the pivot columns, right? Which columns are the dependent variables, and which columns are the independent variables. It's the same thing as we saw in the previous example. In the previous case, when we were looking for the basis for the kernel, we were interested in the independent variables. Here, we're interested in the dependent variables, the pivot columns, okay? And so that's the idea. So let's do an example here and make sure we can kind of see this. So we're going to use our previous example, right? We had a linear transformation from R5 to R4, and we had some A. It was given by L of x equals A of x, right? We had the A, so you can just flip back a couple sections in your notes. But we found that the reduced row echelon form of A, which is the matrix we call B, and it was equal to 1, 0, 0, 0, and then 1/2, 0, 0, 0, and then 0, 1, 0, 0, and then -2, 3, 0, 0, and then you had the last column, which was 0, 0, 1, 0. Right, and so which ones are the pivot columns? So you've got this one, and this one, and that one. Right, so those are the columns we're interested in now. So the, say, non-zero pivots, and then, aka dependent variables, are in columns 1, 3, and 5. Okay, 1, 3, and 5. So these are the non-zero pivot columns, right? You got the pivots. Okay. And so what the method says is, well, okay, now if you want to form a basis for the range, just go grab columns 1, 3, and 5 of the original matrix, and you've got your basis. Right? So the basis So then columns 1, 3, and 5 from A will form a basis for the range. Okay, so in this case, we go back to that matrix, the original A, and you would see that 8, 4, -2, 6, and then 16, 10, -5, and 15, and then the last column 5, which was 0, -4, 7, -7. Right, so those three columns would form a basis for our for the range of L. Okay, and so the dimension here of the range is obviously 3. Right, and so we can confirm, given like the previous two examples, of sort of using these general methods for A, we can confirm that the dimension of the kernel of L would be equal to 2, and the dimension of the range of L is equal to 3, right? And then obviously 2 plus 3 is equal to 5, which is the dimension of R5, the V for the linear transformation. Right, and I think what's great about these examples is that the dimension theorem makes perfect sense when you think about it from the standpoint of the matrix of a linear transformation, right? Because how did we calculate these bases? Right, so how do we calculate these bases? So for the kernel, we get a basis vector basically for each of the independent variables. Okay, right, so that's the method that we just talked through for the kernel. For the range, how did we get it? Where did our basis come from? For the range, we got a basis vector for each pivot, which is basically the dependent variables. Right? For the range, we get a basis vector for each pivot column. Right, so that's of course the dependent variables. So obviously, when you're talking about a reduced or echelon form matrix, you're going to have every column is either independent or dependent, right? The independent variables produce the kernel basis, and the dependent variables produce the range basis. Right? So it makes perfect sense that the sum of those two would be equal to the overall number of columns in the matrix. Okay, and this is actually how things tie into the rank. Okay, so the rank of a matrix. So let's talk through this excellent little theorem here. Okay, so theorem. So if L from Rn to Rm is a linear transformation, with matrix A. Okay. And then we can say that, with respect to any basis for Rn and Rm, like we don't really care what they are. Right? It doesn't matter what A is as long as it represents the linear transformation. Right, so the basis for Rn and Rm is unimportant. Then here's what happens. First, the dimension of the range of L is going to be equal to the rank of A. Okay, so the rank is the number of non-zero pivots. there's a number of ways to think about the range. I think the most prescient way to think about it right now is that it's given a matrix, it's the number of non-zero pivots when we row reduce it, right? So this is kind of obvious given what we just talked through. Okay, and then that means that the dimension of the kernel of L is going to be equal to n minus the rank of A. Okay, so n is the number of columns in A. Rank of A is the number of pivot columns in A. So n minus the rank of A is the number of non-pivot columns, the number of dependent variables. Right, and so as I say, this is actually a fairly obvious result if we, just notice that the dimension of the range is basically given by the number of non-zero pivots, right, which is, basically the same as the rank of the matrix. Okay? And so, yeah, I mean, this is just, in my way of thinking, this is kind of another way of stating the dimension theorem, but this is a way of stating it that is a little more specific to the idea of a linear transformation and the matrix of the linear transformation, right? So when you're talking about linear transformations without the matrix, then this is not a convenient way to think about it. The dimension theorem makes more sense. But if you know what the matrix of the linear transformation is, then this is a much more convenient way to think about it. Okay. All right, and so we're not going to prove this one, but I think you guys could prove it pretty easily given just the setup from the previous couple of examples. You can kind of generalize those and prove this one, I think, pretty easily. Now there's a quick corollary here that is kind of is a beauty actually, but it's real specific, and so what it is it's the well, I'll just write it out. So if A is any matrix, right, dimension's not important here, then the rank of A is equal to the rank of its transpose. Right, now that may not be obvious, right? If A is an n by m matrix, then A transpose has fewer columns, right, or more columns. It has a different number of columns. So how can the rank necessarily be equal? And so this is something that would be very challenging to prove probably without the previous theorem, but it comes quickly given the previous theorem. So let's prove this one, and we'll kind of wrap up this lecture with this proof. Okay, so let's let A be m by n. Let's let A be an m by n matrix, and then let's think about A as being the associated matrix for a linear transformation. So let's consider, how can we say that? Let's consider L from Rn to Rm given by L of x equals A of x. Right, so i.e., all I'm saying here is that A is the matrix of the linear transformation. Okay, and so what can we say? Well, we know from what we've just been discussing, we know that the range of L, the linear transformation L, is equal to the span of the columns of A. Okay, and what does that imply? Well, that implies that the range of L is the span of the rows of the transpose of A. Right? Okay, and so what does that mean? Well, that's just another way to say that is the range of L is equal to the row space of A transpose. It's equal to the row space of A transpose. Okay, and so what we can, just using the previous theorem, we can say then, therefore, the dimension of the range of L is equal to the rank of A transpose, right? That follows immediately. Okay, but also what do we have? Right, but also what do we have? We have the dimension of the range of L equals the rank of A. Okay, so both are true, right? And so obviously we can equate here, and so that's going to imply that the rank of A equals the rank of A transpose. Okay, and we're done. That's it. Right. It is straightforward given the setup from the previous discussion. Okay, very good. So I think we'll end it there. And obviously that was a very dense section. This whole subset of lectures on linear transformations is very dense, I think. It's among the hardest sections of linear algebra. And then the next lecture is no exception. We're going to talk about isomorphism in the next section. So until then, take care. And again, make sure you go back and make sure you're following the proofs. And if my explanation isn't satisfactory, a lot of these proofs you can look up online pretty easily. So do so if just to make sure you understand the reasoning. I wouldn't expect anybody to necessarily be cranking out the proof of the dimension theorem. But you should be able to follow the twists of that proof. So, all right. Until next time, take care, and we will talk to you all next time. Take care.